So, welcome to the pirate class, Operational Technology Security. This is not an official college class and it's not worth any college credit, although perhaps someday it will be added to the curriculum, but in the meantime I need to know it, and I think it'd be good for you to learn if you have enough free time to learn something that's not directly contributing towards getting a degree or certificate. A lot of my students are in fact like me. I know they've got a job, they've got enough degrees, they're taking these courses just to learn, not particularly to get another degree. So, all right, so operational technology is the hardware that controls physical processes, and it is very insecure, as we're going to explain. And we're going to talk about how to try to secure the modern networks where you have OT plants like water plants, that news article, that are connected to IT systems like Windows and TCP/IP networks and servers and stuff. And unfortunately, that means they can get hacked through the TCP/IP system, like Iran did to the water plant in Pennsylvania. And so defending them becomes very important. So I found a textbook. It's not a very good textbook. I don't much recommend buying it. For example, there are no figures at all. It's only text. And each chapter seems to rephrase and state things that have been previous factors differently. And so my impression is that this field is in a state of flux and chaos. Even what apparently would be foundational things like the Purdue model we're going to talk about appear in different versions from different sources. So this is something I've gotten used to ever since I started teaching security and hacking. In early stages, a field is kind of a mess. The rules aren't really standardized, the tools aren't really standardized, the concepts aren't really standardized. So you just jump in and try to organize it, but be prepared for a bit of chaos. And so I made summaries of this textbook, and that's all I would do if I were you. I wouldn't bother buying it. Anyway, we'll talk a couple of chapters from that book every week, and then some hands-on projects, which you'll find down here. And there's an automated scoreboard to submit the projects. And I think I also have a canvas with quizzes in it. And don't turn in your projects there, just use the automated scoreboard. Anyway, so that's what's going on. It's only 6 weeks long, and let's jump into it. So, the first chapter, I think I'll just go right into that. Won't bother to make a separate video of course metadata, because there really isn't much course metadata. All right, so operational technology is technology that interacts with the physical world with things like motors and valves and switches, controlling something like factory equipment, industrial equipment, energy power plants, healthcare, and so on. So OT is different than IT. Operational technology. IT is information technology, the stuff that all our other courses are about. Web servers and Linux boxes and all these things. So we're going to talk about the network infrastructure and the applications and so on. So the first concept is OT is concerned with physical processes like manufacturing and power generation. So it's got sensors reading pressure and temperature and motors moving machinery around and such. IT is the stuff we're used to, computers, software, network, and systems, handling information to make decisions, but not usually connected to mechanical objects to any significant extent. So OT is on the factory plant floor and directly manages industrial activities, and IT is in offices, and it's about using databases, email, and so on that we're all used to. The desk jobs for people that sort of keep their hands cleaner and work in offices. The problem is they're now converging. It turns out that the factories run much better when processes are automated, and so they develop these OT systems to automate the process, and now it turns out, just like in every other part of technology, it's much better to have it all connected to the internet so you can manage it remotely instead of having to drive on site to handle all your problems. And so the efficiency improvements by connecting the IT to the OT are so large, people are doing it, even though it causes security problems. So in IT, our security priorities are confidentiality, integrity, and availability. That's the three essential pillars of information technology security. But in OT, the priorities are safety, reliability, and productivity. A very different set of goals, and that is at the heart of the problem. So the network infrastructure is designed to control sensors, which are things that read something, like whether a button is pressed or whether a temperature is at a certain level. Then actuators are outputs, things that do something, open a valve, turn something on and off. And then control systems are things like the industrial control system devices that send signals to these. And you often have a small local area network to control the operation within one room. But now we have multi-site networks or even whole geographical regions all being controlled by these networks sprawling across. The protocols used in OT are not TCP/IP or anything like it. They're different other protocols. Common ones are Modbus, Profibus, and DNP3. And these are designed for reliability and real-time communication, and they typically have no concept of security at all because they were intended to be run just on a local area network within your factory, and there is no passwords or encryption or authentication of any kind because simple physical presence in the room was considered sufficient authorization to operate the device. So, but now we got TCP/IP coming in, so you can do advanced data management and control these things over a larger scale, but that means the OT systems are now exposed to cyber attacks, which these protocols were never designed to tolerate. So the OT network architecture is hierarchical. You've got field devices, the actual equipment, then you've got control systems that control the equipment, and then you have enterprise systems above that, which are above the control system and operate at a higher level. So here's some factors. You want determinism. You want to make sure that when you have the same situation occur, the same result will happen every time. You want to control the latency, the time between issuing a command and the actual result of it, and you want to minimize jitter, which is the variation in latency. So the Purdue reference architecture is what takes the place of the OSI model in IT for OT. They use this thing called the Purdue reference architecture, which does not seem to be terribly well standardized. But you've got low levels here with the sensors and actuators. Then you've got manufacturing operations and controls. This is, I think, where the SCADA layer is, supervisory control and data acquisition. And up here you've got the normal IT stuff we talk about, business planning and logistics, enterprise resource management. That's one structure of the Purdue model. So the protocols. These three protocols give real-time, reliable communication. They're very simple, very lightweight. They require minimal computing power because they're intended to run on equipment and are designed for really old equipment. And so they're intended to be very simple systems. Modbus is the oldest from '79. Profibus came a little later and is a little more complex. And DNP3 is more robust and common in utilities like electric power plants. So make a hierarchical structure here in your Purdue model. At the lowest level, you got sensors and actuators, and then control systems here, and then up here, data analysis and process operation at the enterprise level. All right. So the need for speed and precision. So you need real-time control, you need low latency, and you need to minimize jitter. That's what you need for your OT network. All right, and then reliability. OT systems operate in a harsh environment. You're likely to have big, heavy factory equipment breaking, water spilling around, extreme temperatures and so on. So you have to plan for all these contingencies, especially since you're just going to keep this stuff running for year after year. Sooner or later, something's going to break. So you have to consider all these bad things that can happen. So you have redundancy, backup systems to take over when the first ones fail, and you have diversity. Use different devices from different manufacturers with different technologies so that if one has some kind of systematic flaw, the other will hopefully not have the same systematic flaw. All right, and so these things are applied in all sorts of industries like manufacturing. And if you automate it, then it's more likely to be easy to control the quality and predict when things will fail. And you can have fully automated production lines like Tesla does. And in energy, you control the distribution of electricity, nuclear power plants, wind farms. In transportation, your traffic management systems and signals and so on. And air traffic control at railways and airports, and railway control. All these things are done with OT systems. And oil and gas creation and distribution is all done with OT systems. And healthcare manages automated devices for environmental control and patient care. So what hardware had the OT network used before Ethernet? I don't know what the actual physical hardware of the lines is. I think it's just straight serial cables in some cases. It's a good question, and I don't really know. It's all new to me, and I'm just figuring it out. Now, I've got some cahoots, but I have to step away a few minutes before we do that. Let's take a 10-minute break. I'll pick up at 9:30. I'm going to stop the